Today's problem is submitted by a viewer, and it says, suppose xn is a Cauchy sequence such that for infinitely many n, xn is equal to c. Using only the definition of Cauchy sequence, prove that the limit of xn is equal to c. So xn is equal to c for infinitely many n. We need to prove that the limit of xn is equal to c. Okay, so my first thought here is that if a limit does exist, it has to be equal to c. Because if the limit were anything other than c, then there are always terms that are far away from whatever that limit is. So you're infinitely often some distance away from that limit. So the limit can only be c. It's a Cauchy sequence. So I mean, I think this kind of just falls out now that I've written down more or less, I haven't written down the complete statement, but more or less the definition of a Cauchy sequence. Okay, so how do I want to structure this precisely? Okay. Let's let epsilon be greater than 0. Okay, we're going to let m be sufficiently large so that xn minus xm is less than epsilon for all n and m greater than capital M. So that is here. This is we know we can find this because we're given that x is a Cauchy sequence. In particular, xn minus c is less than epsilon for all n greater than or equal to m. So this is true for all indices greater than capital M. We know that there's always an index greater than capital M where xn or x little m is equal to c. So I can always find a little m where this is equal to c. So choose that value of little m. Then I have that this is true. And we're done, aren't we? Right? We have an arbitrary epsilon greater than 0. We found some value of capital M, and it will satisfy this. And so that's just the definition of the limit of right? If I put that statement together with that, that's the definition of this limit. Yeah, so I thought maybe there'd be a little bit more to this. I thought maybe I would have to use triangle inequality a couple of times, break things up, break this up into a distance from xn to c and a distance from xm to c. But I don't think that's actually necessary. I don't see anything that's wrong with this proof the way that I've written it. So yeah, I'll just leave that. I'll leave that as it is. If I have more to say, I'll put it down in the description, and leave a comment if you've got more to say about this problem. Thanks for watching.